In section 3.4, we're going to be talking about equivalent transformations. Can different transformations produce the same result, essentially? So let's just do a quick little review here. Write the rules for the coordinates in the following transformation to the graph of f, right? What happens to every coordinate on the original function? All right, well, let's start on the inside. That's where I like to start, right? F of what? It doesn't say f of x. It says f of something else. These are my horizontal changes. And we said horizontal transformations. You do the inverse operation in the reverse order of operations. Typically, we would multiply before we add. Well, we're going to reverse that. We're going to deal with the addition and then the multiplication. So we know we need to, if it says 3 times x, we're going to be multiplying by 3. And if it says, if it says 3 times x, we know we're going to be dividing by 3. And if it says plus 4, we know we're going to be subtracting 4. But remember, we're going to do the subtraction before the division. So I'm going to take x and subtract 4. And I'm going to take that answer and divide by 3. That's how I'm going to find my new x coordinates. So that just took care of the inside, right? Now remember, f means y. So then everything else we just write down. We take this f of whatever, which means our y value, and so it's negative 1/2 y plus 7. Nothing changes on the outside. Okay? All right. So it says, can two different transformations produce the same result? So let's start with the graph y equals x squared. Lovely little parent graph. It says, write the rules of the coordinates for each transformation. So this first one says y equals 9 times x squared. So here's my function, x squared. That's like my f of x, and they want me to multiply it by 9. That 9 is outside the squared, right? And for, when would it look like if it's inside? Well, then they'd use parentheses and put it inside. So that means any point on the parent graph xy will become x comma 9 times y. This is a vertical stretch by a factor of 9, right, if we're thinking about describing the transformations. Okay. On the next one, we still have something squared, but notice we're changing the inside. And this says 3 times x. Well, we're going to do the opposite of that, and we're going to do x divided by 3. Right, but there's nothing outside the squared like there was here with the 9, so it's the only change. This is a horizontal compression, right, by a factor of 3, or I guess we could say factor of 1/3, right? We're cutting it down in thirds. Well, it says simplify both equations and compare the results. There's honestly nothing to simplify here. 9 times x squared is just 9 times x squared. But here, when we have 3x, quantity squared, we know that means 3x times 3x, or 3 times x, which is 9 times x squared. Isn't that the same thing? So we could look at this two different ways, and it's really a personal opinion. We could consider this a vertical stretch factor, right? Do you want to multiply the y's by 9? Or would you prefer to look at it as a horizontal compression, dividing all your x's by 3? It will produce the exact same graph. These are equivalent transformations in this case. Okay? So let's take a look at this next one. It says determine the parent function, then graph the function in two different ways. Okay, well, y equals the square root of x is my parent graph, right? There's an extra 4 in there. We'll deal with that. Well, I guess we'll deal with it now. One option is to look at it, it's on the inside, it's with the x. So we could, by the way, our parent graph goes through 0, 0, 1, 1, and 4, 2. We did that the other day. We could look at that as a horizontal change. And if it says x times 4, then we're going to do x divided by 4. So 0 divided by 4 is 0, 1 divided by 4 is 1/4, 4 divided by 4 is 1. Thank you. The y's are going to stay the same. So 0, 0, 1/4, 1, and 1, 2. Whew! I should maybe draw in our little parent graph here. So there's my parent graph. Okay? Or, what if we simplified this? What if we took this 4, we took the square root out, right? We know the square root of 4. And now we don't have a horizontal transformation, we have a vertical transformation because now that multiplier is on the outside. Means the x's stay the same, but we're going to multiply the y's by 2. So let's see, 2 times 0 is still 0. 2 times 1 is 2. 2 times 2 is 4. So here we have 0, 0, 1, 2, 4, whoops, 4, 4. And again, here was my parent graph. I mean, when you look at it, aren't they the same? Right, they're the same red graph. I mean, I know I didn't have that 4, 4 there, but we got there differently. Now, it's not always going to be an option, but it's something interesting to consider. Sometimes you might want to simplify your function because maybe it'll make it easier to graph. Right here, I mean, not that that was horrible, but look, a little fraction there wasn't maybe as accurate as we could have been. Okay, same graph, but we looked at the transformations differently. Okay, all right. Let's move away from some square roots. Let's look at some exponential expressions. It says use properties of exponents to show that each statement is true. I want to show that this is really the same as this. How do we show that? We simplify one side. Simplify one side to match the other. Well, honestly, I think this side maybe looks a little messier. So maybe we start over there. Well, I don't know, when you have addition in your exponent, we could write that as 2 times 3 to the x times 3 to the first, right? If the bases match and we're multiplying, we add the exponents, we could reverse that. Maybe I picked the harder side to deal with, I don't know. Well, 2 times 3 is 6 times 3 to the x. They match, right? I was able to turn this side into this side. So the point is, if you had to graph this, you could simplify it first and maybe graph an easier version of it. Okay. Let's take a look at this one. It says 3 to the 2x equals 9 to the x. Maybe we start on this side this time. Doesn't matter. We did a little bit of this in our homework. 9 can be written as 3 squared. And when I have an exponent raised to an exponent, we multiply the exponents. Now this side and this side are exactly the same. So we've shown, there's no answer here. They gave us the answer. We're just kind of proving that they are the same. Okay, so just kind of thinking about some of those properties of exponents and breaking things down a little bit. All right. So it says, let's consider this function, k of x equals 3 times 2 to the x plus 2. Part A says, describe the transformation from the parent graph, y equals 2 to the x, to this graph right here. Write the rules for the new coordinates. Well, first of all, notice it doesn't just say x, it says x plus 2. That's a change to the x. So the rules for the coordinates, I'm going to subtract 2 from every x. This graph is going to move to the left 2. And then outside that exponential, it says times 3. So we're going to multiply all the y's by 3. So it's a vertical stretch, and we're going to move the graph to the left 2 units. That's fine, no big deal. Well, now it says rewrite function k so that you only need to do one transformation. Instead of doing 2 steps, can we clean this up? Well, let's take this. 3 times 2 to the x plus 2. Addition in my exponent means it used to be same base with multiplication. Well, I like that. So I have 3 times 2 to the x times 4. And 3 times 4 is 12. So it's still the same parent graph. It still says 2 to the x, but now I don't have a horizontal transformation in there. The only thing I have to do is multiply by 12. So x's are going to stay the same, but I'm going to multiply the y's by 12. That's a personal opinion at this point, but these should produce the same graph. I mean, we start multiplying by 12, our values might get pretty large, so that's kind of something it's a trade-off, I guess. So it says check by graphing both in the same viewing window. So I'm just going to go graph these. I'm going to graph 3 times 2 to the x plus 2. And I'm going to graph my simplified version, which is 12 times 2 to the x. Whoops. I know you didn't really see anything happen because, well, it graphed the orange graph right on top of the green graph. So we've just shown it's the same graph. That's what we wrote down. That's what we were crossing our fingers for. Okay. All right. So g of x is still that parent graph 2 to the x. It says describe the following transformations to the graph of g. So let's talk about this one here. Whew. So it's not just 2 to the x, it's 2 to the 3x plus 3. There's my horizontal changes. Those are where x used to be. And then outside of that exponential, that's the vertical change. All right, so here we go. My coordinates, x, y. This is from the other day. We have to divide by 3 and subtract 3. Remember, we deal with the subtraction first. We're going to do x minus 3 divided by 3. And then all the y's are going to get multiplied by 3. Coincidentally, that's a lot of 3's. I didn't mean for that to happen. So we had a horizontal shift, a horizontal compression, and a vertical stretch. 3 transformations. That's fine. We did it the other day. But now it says let's rewrite the equation. Let's simplify this and then talk about the transformations. So let's clean this up. So I have 2 to the 3x times 2 to the third. Right? The addition here turned into 2 factors with a base of 2. 2 cubed is 8. 8 times 3 is 24. I'm not done yet. I'd love for it to just say 2 to the x, right? So, or something simpler maybe. So I have 2 to the 3x. Could we write that as 2 to the third all to the x, right? Because we'd multiply that and get 3x. Well, 2 to the third is 8. So here's the kicker. It looks much simpler, but we have a new parent graph. That's okay. I'm okay with the fact that I have a new parent graph. So I would go graph y equals 8 to the x, but I only have one transformation, and that is to multiply the function by 24. So x's don't change, the y's get multiplied by 24. I think that's a lot nicer than doing all of this. It's a personal preference. Okay. All right, last one. So here we have f of x equals 3 times 4 to the x. It says describe the transformations for each graph here by writing the rules for the new coordinates. So they want me to take f of x and divide by 4. All right, well, that means take y and divide by 4. So x, comma, y over 4. Okay. Well, this one says take a f of x and turn it into f of x minus 1. Well, the only change there is that we're going to add 1 to the x's. So we're going to take this graph, cut the y's down by 4, or take this graph and add 1 to the x's, move it to the right one. Completely different transformations. Are the transformations equivalent? Well, let's find out. Let's take f of x and let's divide by 4. That's like 4 to the first, isn't it? So let's see. We've got a rule for that, right? We're dividing with the same base. Let's subtract the exponents. Let's look at this one. This says if this is f of x, then f of blank equals 3 times 4 to the blank. If they want me to find f of x minus 1, let's put a minus 1 in there. Oh, isn't that the same? So yes, the transformations are equivalent. Wild, isn't it, that moving this graph to the right one is essentially the same as a vertical compression. Just interesting.